Have you ever wondered how fast your cat can run? Can they outrun a swarm of bees? Have you ever bought a toy for your cat that they ignore, but you think they use in secret? Do you need a clock with a chain for a face for your house? Hi, I'm Ronnie, and that was Patky. And in this video, I will talk about a machine that I built that can answer at least some of these questions. I will explain the principles behind gear ratios that I use to calculate how far the cat runs when this wheel is turning. I will also talk about train wheels and their conical shape and how I use this principle in the cat wheel. And I will also give away a clock. So if you want answers to these questions that I know all cat owners have, or just want a really unique clock for your house, this is the video for you. To make something like this looks really complicated. But like most complicated things in life, it's just a series of small and simple things that's put together that makes the final product look complicated. This is the same with most math problems, and I will break down the math that was needed to make this wheel in smaller steps that's really actually quite simple. The first thing that I will start with is the size. How did I decide on the size of a cat exercise wheel? And what's a general rule that people need to know about when they decide to buy a cat exercise wheel? Some people say that the inner diameter should be at least 1.5 times the length of the cat. Some people say it should be 48 inches for adult cats. I think that bigger wheels have a shallower slope, and this means that the cat's spine will be less stressed when they run on the inner surface. I measured Donkey and I decided to be on the safe side, I'm going to make it double the size of Donkey, which is just under 1 meter. So I rounded it up to 1 meter because it feels easier to work with round numbers. Now that we know the inner diameter of the wheel, we can calculate the circumference of the wheel. And this is really quite simple. There's a formula. But since the diameter is 1 meter, the formula reduces to something even simpler. The circumference is pi. Nobody knows the exact numerical value of pi. Some people know a small bit in the beginning. I personally just look it up every time I want to use pi. And for our purposes, 3.1 is fine. So we know that if the wheel turns once, the cat has run 3.1 meters. Now that we know this, we can make something that shows us how far they run, basically an odometer that counts how far the wheel is turning. To do this, we need to build a small machine, and since we like to work in base 10 or the decimal system, we want every digit to show us how many tens we have. So the display wheels should have 10 sides. So as the cat runs, we want the values on the odometer to change to one more digit for every meter that it runs. This sounds a bit complicated, but it's actually not. We will use a bit of math to determine how much the big wheel turns and then how much the smaller wheels turn that will drive the gears that turns the odometer. To figure this out, we first look at the number of times the small wheel on which the big wheel runs rotates. The reason for this is the small wheel is connected to a rod, and on the rod there's a small gear that will drive the gear reduction system. So if we know the number of rotations, we know how many gears we should place before the odometer. We know the outer diameter of the wheel is slightly larger than the inner diameter, which is 1 meter. So it is 1.08 meters, and the small wheel on which it runs is only 36 millimeters. To determine how much the small wheel turns, we just divide the big number by the small number. So basically it's 1.08 meters divided by 36 millimeters. And we get a number of 30. So the small wheel turns 30 times every time the big wheel makes one rotation. Now that we know how many times the small wheel turns every time the big wheel turns, we want to convert this into something a bit more sensible. How many times does the small wheel turn when the cat runs 10 meters? So first we need to determine how many times the big wheel turns when the cat runs 10 meters. And we know the inner circumference is pi. So every time the cat runs 3.14 meters, the wheel rotates once. So to determine how many times it does in 10 meters, we take 10 divided by 3.14, and we get the number of times the big wheel turns when a cat runs 10 meters. Then we just times that number, which is 3.18, by 30, and we know how many rotations there are for every 10 meters the cat runs on the small wheel. So basically, if we do all the math, we see that for every 95.4 rotations of the small wheel, the cat has run 10 meters on the inner diameter of the wheel. From this, we can determine what we need to do to make the gear reduction system count only one rotation for every 10 meters. And this works on the principle of gear reduction. So an example is if we have a gear that has 60 teeth and we have a gear that has 10 teeth, every time the small gear rotates 6 times, the big gear will rotate once. We use this principle to determine how the gear ratios should look to connect the odometer. An easy solution would of course be to make a large gear of 954 teeth and a small gear of 10 teeth, and then we have the gear reduction of 95.4 to 1. But such a big gear is impractical and it is just too big to fit into the machine. So a different way of doing it is making a series of gears and then just multiplying the gear reductions until you get to something that you want. Now, 95.4 is a difficult number. It doesn't divide properly into full numbers. You cannot have fractions of gears. But a very close number is 96. So I rounded it up, and there will be a slight underestimation of how far the cats run. But if we use 96 to 1, the gear reduction system can be made by using 3 sets of wheels, one set of 40 to 10, another set that's also 40 to 10, and the final set of 60 to 10. And then to get the gear reduction, we just edited Ronnie here. I made a small mistake explaining. You divide the product of the large teeth by the product of the small teeth. So it's 96,000 divided by 1,000. So then we have 96 to 1. Now all this calculation just means that when the small gear turns 96 times, the last gear in the reduction system will turn only once. So which basically just means that when a cat runs 10 meters, the rotation on the output of the gear reduction system will make one full rotation. And if we have a disk that displays 10 values, each spaced 1/10 apart, it will count 1 meter every time the cat runs 1 meter. And this is exactly what we want. It's of course a wooden system and there's a bit of rounding here and there, so it's not accurate in any sense to do scientific experiments with, but it's close enough for what I want to do. And I am quite happy with how well it functions. I also included a direction rectifier. This is a term that I made up for a small machine that makes sure that every time the cat changes direction, because they do not necessarily run in only one direction, it makes sure that the output that goes into the odometer is always counting up. I don't want the odometer to count down. So now we can answer the question, does the cats use the wheel when we are not looking? Because it will count up every time they use it. And the answer is not really. Camille does use the wheel sometimes when I'm not looking, but she takes a few steps and then she goes away. I know this because I can hear the wheel when it moves, and Perky does the same. Donkey, of course, never uses the wheel, but I think that in the future, or when it's colder and they are inside more and they have more energy, they will start to use the wheel a bit more. The next thing we needed to calculate is how fast the wheel turns. And luckily, this is a much simpler calculation. So the idea behind this is we have a needle that points at a certain position, and we want to know how fast the wheel turns when the needle points at that specific place. So we can measure how far the wheel turns by the use of the odometer in a specific time. And if we rotate the wheel at a constant speed and mark where the needle is, we can determine the speed that the wheel is turning at that position. So we measure it for 10 seconds. And since we know the distance in meters for every 10 seconds, we can easily calculate the meters per second. And since I'm more familiar with kilometers per hour, I converted it. And the conversion is really simple. You take the meters per second value and you times it by 3.6. So now we can answer the question, can you outrun your cat? And from this exercise wheel, I cannot answer this question because it only goes up to 9. And sometimes Camille runs faster than that. If you go onto the internet, you can find this answer really easily. You don't need to build this excessive machine to try and answer this type of questions. A cat can run at approximately 48 kilometers per hour, and that's a normal house cat. Usain Bolt, the fastest human, can run 44.72 kilometers per hour, so most average house cats can outrun Usain Bolt. An interesting note is a bee can fly up to 32 kilometers per hour, which means that the average house cat can outrun a bee without any problems, but the average human will probably not be able to do this. Most fit athletes can make it usually up to around 25 kilometers per hour, but most of the people that I know, including me, will not make that speed, so there's no point in trying to outrun a swarm of bees. I can answer how Camille is performing on this wheel, and it depends on what we're doing. If I give her treats, she usually walks a bit slower, so if I have a treat in my hand, she will walk between 3 and 5 kilometers per hour quite constantly to get to my hand to get the treat. If I play with her and she's chasing things, the speed fluctuates a lot. It goes up to past 9 kilometers per hour. I guess about 15 kilometers per hour if she jumps on the side and it rolls down very fast. And then usually she stops and waits a second or two, and then she runs again. So that's really high speed, but it's not maximum speed. I do not think cats can run up to their maximum speed in a cat wheel. It's not a flat surface, and there's always something obstructing their view. So I think they're always going to jump or jog at most, but never run up to 40 kilometers per hour. I mentioned train wheels several times, and the reason why I mention it is because train wheels, like the small wheels in my exercise wheel, are conical. The reason for this is the conical shapes help to keep the wheels on track, and there's a lot of nice videos explaining this principle. Train wheels have a slope of, I think I read 1/20, so it's quite shallow, and the wheels that I made have a slope of around 1/9. The reason for this is just because I thought it looks cool, and since it works well enough, I'm quite happy with it. I should mention that here I made a small mistake. I calculated the center of the wheel to be 36 millimeters, but the big wheels are flat on the bottom, and of course they run on the edges, not the center, so the calculations are off by a factor of 1.08. An easy fix would of course be to make the wheels smaller. The small wheels rotate slightly less than 95.4 times. I did take this into account when I calculated the speed, so the speedometer is more accurate given all the other inconsistencies in this exercise wheel. There are of course a lot of other interesting calculations in making a wheel like this, but I think these were the most important ones. If you're still watching, please consider subscribing. And if you want to stand a chance to win a clock with a wooden chain for a face, there are 2 things that you need to do. First, subscribe to this channel. And second, leave me a comment. I will contact the person with the most upvoted comment and I will ship the clock out to you. In the next video, I will start doing this with strandpiece kits, so stay tuned for that. The plans for many of these things are available in the description below. This includes the cat wheel, the odometer, the chain clock, and a variety of other things. So check them out if you want to build your own. Thanks again to the Patreon members for making it possible for me to build this wheel, and thanks to you for watching. See you in the next one. Cheers!